CO2 in the depleted oil and gas fields to have basically almost CO2 neutral hydrogen coming from natural gas. And we're also looking at other concepts like platform electrification to reduce CO2 emissions from oil and gas production on the short term. And we also look at energy storage concepts. But today the focus is on hydrogen. So why hydrogen? Basically, for North Sea and for the Netherlands, where this energy program has started, is that we see a lot of potential for offshore wind. If you look at system analysis for the Netherlands, we really need offshore wind to make the Paris goals at 4. If you really reduce the amount of offshore wind, you will really increase the cost of reaching Paris targets by billions a year. So that is crucial in our energy transition. And now we have about 1 gigawatt of installed capacity offshore. And it's going to grow fast towards 11.5 gigawatts in 2030. And there are plans or system models that say we're going to grow to, let's say, 60, 70 gigawatts of wind in our part of the North Sea. And in such a scenario, you should think of hundreds of gigawatts of being installed in the entire North Sea of Norway, the UK, Denmark, Germany, etc. As you can see here in the bar, you will see that offshore wind is going to grow to be the biggest electricity producer in the Netherlands. It's going to be dominant. And as we can also see, we think, although we're also looking at bringing offshore wind as hydrogen to shore, as I just showed, we think that the larger part will be brought to shore as electrons. So the real premises of the energy transition is if you can use electricity, use it. If there are other rightful uses, then you have to can convert it into hydrogen. So when looking at hydrogen, it's very important to understand that we are looking at a mix of hydrogen in the Netherlands and not just only the green hydrogen. Because if you look at the future cost estimates for the energy transition, it's probably a cost-effective method to move into a mix. It increases your security of supply, but it's also cost-wise is attractive to have a mix of blue and green hydrogen in your system. We overall see that in these future energy scenarios that hydrogen has an important role to play, although they differ between the scenarios, but I'll come to that in the next slide. And what we also see is that we see opportunities for moving hydrogen production offshore, because we can save then on electricity grid costs. We save a lot on electricity cables that have to be brought to shore, and that has to cross dunes in the Netherlands, and you have to cross expensive crossings and densely populated areas. So you can avoid basically grid congestion and grid access costs by converting already the hydrogen offshore. And we also see that you have additional synergy between green and blue hydrogen, as you can use, for instance, the oxygen from green hydrogen production in blue hydrogen production, and you can also use a little bit of the heat from the green hydrogen production, maybe onshore in your energy system. So we believe that the future has a mix of blue and green hydrogen, as that's the most cost effective. So how do we get there? Current demand in the Netherlands is about 1.8 million tons of hydrogen. Just to put it into perspective, we think that recent literature suggests that there's about 60 megatons of global hydrogen production and demand. So we have some share in the Netherlands, but not too big. Almost all of our hydrogen is being consumed in the industrial clusters, which you can see here on the map, and predominantly the Rotterdam, or our big harbor and refinery cluster, where ammonia and refineries use this hydrogen for refining processes. And we have ammonia producing plants here in Zealand and in the southern part of the Netherlands, which also use a lot of hydrogen. But in the future, we also anticipate that there will be more industry, so feedstock and heat being used by hydrogen. Mobility is going to increase probably, the built environment perhaps, and we also see a role for it in the power sector to be a peak supplier in times of low wind and low solar. And what you also can see here on the map, you see the vast infrastructure we have in terms of pipelines already offshore and onshore. And you can also see where the wind areas are being projected. So you can clearly see that there's some synergy between existing offshore pipelines for natural gas now, but perhaps in the future for hydrogen, and the wind areas that can deliver this electrons to convert hydrogen. So what if you look at the hydrogen supply and demand in 2050? In this slide, we compared some future scenarios, and this is just for the Netherlands. And there's no need to take a deep dive into all the graphs, but just the key takeaways is that the hydrogen demand and supply really differs depending on your system choices you do in those scenarios. So what do you think is the role of other flexibility options such as biomass, import of energy, but also other renewable energy sources to meet your Paris targets? But that's one point. If you look at the breakdown of these scenarios, so where is the hydrogen going to? It seems that industry is a very robust sector for starting up processes, as you can use basically green and blue hydrogen as a drop-in for the existing gray hydrogen. And other purposes you see coming online in these scenarios are the transport, which is also quite stable but significantly lower compared to industry. And we can see that the built environment and the power sector really depends on what kind of system choices you make in the scenarios. So this holds for the Netherlands, but it will also hold for other parts of Europe, we believe. And one of the big wildcards is synthetic fuels. You can see here in the bars, this is the turquoise or the blue bars. So if the studies assume that we're going to make synthetic fuels with hydrogen, and the fuel production is a big sector in the Netherlands, in the Rotterdam area. So if you believe that that will be replaced by synthetic fuels, then we're going to use a lot of hydrogen. So that's the big wildcard in scenarios. So what in our North Sea Energy program, what did we study? So basically we took one of our scenarios to explore what the role is of offshore hydrogen production. And here you can see in one of our scenarios what this mix would be in 2050. So it's almost a balanced mix between onshore blue hydrogen. Here it's about 40 terawatts hour of hydrogen. And here you can see also the offshore green hydrogen, which is a relatively big part of the total production. And offshore green hydrogen. And remarkable here is that in this outcome is that the offshore green hydrogen is bigger than the onshore green hydrogen. So we really think that there are opportunities for moving the hydrogen production offshore. But I have to say that comes with a disclaimer. It is very important to understand that if it's interesting to move hydrogen offshore to maybe, for instance, on offshore platforms, existing oil and gas platforms, or to be newly created platforms, or on an energy island, really depends on how far away are your offshore wind area, the new offshore wind farms, and also a factor of capacity. So if you go towards bigger capacities, it's interesting to move into the hydrogen production, as you can transport hydrogen cheaper than electricity to shore. So capacity plays a role, distance plays a role, as again, transport of hydrogen is cheaper. So if you want to convert it for hydrogen, then it's if you go further away, then it's a lower cost. But the difference in cost between having it onshore or having it offshore really depends on whether you think is the total cost of installing it on an energy island, for instance. If you believe that it is much more expensive than onshore, then the tipping point goes to onshore, and that is around a factor of 1.5 to 2. So if you believe that offshore hydrogen is 2 times more expensive than onshore production, then the tipping point heads towards onshore. So to come to this assessment, we have also our partner Bilfinger, who's presenting later today, designing an offshore island. And here you can see an artist impression of that. And basically, with this concept, we studied a 2 gigawatt energy island, a 5 gigawatt energy island, and a 20 gigawatt energy island to see what the effect is of scale. So again, we believe that a big part of the hydrogen production can be brought onshore, so about 50% or more even from the total production. But this is very dependent on cost assumptions. So just to give you one breakdown of such an energy island, here you can see the total capex of an energy island we studied, and in this variant we used a 5 gigawatt wind connected. So it's 5 gigawatt wind farm connected to this island, and 30% of the hydrogen, 30% of this electricity is converted into hydrogen. So the total cost of this structure is really dominated by the hydrogen conversion cost. You can see here, that's a 46%, and of that total 46%, hydrogen production dominates it. So the hydrogen transport, so the pipelines and compression, that's relatively limited. Really the capex of your electrolyzer dominates the cost. And if you look at the total island, you can also see that the structure, so the actual island, coming to 900 million euros, is not dominating the total cost. It really is the infrastructure that you put on the island that dominates the cost. So that's an important outcome of this and past studies. And if you look into what the cost will be of bringing the hydrogen to shore, we think that if you have, it's really a balance between the hydrogen price and the electricity price, of course. But at hydrogen prices around 4 euros, you could be already have tipping points. And that's 4 euros per kilogram, by the way, sorry. So if we were going to move to that in 2050, of course, we really have to test this first. And that's why also as a spin-off project from the North Sea Energy Program, the Poseidon project is being developed. And this is worldwide unique. It's the first, as we know, of offshore production of hydrogen using a 1 megawatt electrolyzer to be put on a platform, as you can see here. And this is just an existing and operating oil and gas platform off the coast of The Hague in the Netherlands. And it basically is electrified by a cable coming from onshore. And we think, at least we hope, that already the production is going to start in 2021. So that is next year. But it's going to be a tough timeline. So the lessons learned from this project is, of course, that how do these electrolyzers operate offshore? What are the lessons learned if you operate it on a variability and under the harsh offshore conditions? That's the unique lesson we're going to learn here. So that was green hydrogen, but also blue hydrogen has a very important role, we think, as I just shown earlier in the Netherlands. Basically, in our energy system analysis, we show that if you reduce CCS, so if you reduce the ability to capture, transport, and store CO2 from hydrogen and other industrial processes in the Netherlands, you increase the societal cost of the energy transition by billions per year. So we believe that CCS has a role to play, especially together with blue hydrogen. And here you can see a map where we think how this is going to work. Here you can see the large industrial clusters in the Netherlands. So this is Rotterdam, Amsterdam and Harbor, Den Helder and Harbor, and the North Netherlands and Harbor. And those could be also clusters where CO2 is captured from blue hydrogen production, but also other industrial processes, and then move to offshore depleted oil and gas fields, which are shown here as bubbles indicating storage capacity, and to move the CO2 here and store it for decades and millennia. And what it also offers to the energy system in the further future is that you have a network and a system to enable so blue hydrogen, but also perhaps negative emissions as being suggested by the IPCC also as one of the future options to go carbon to reduce CO2 emissions from sectors that cannot reduce CO2 emissions easily. One of the benefits, of course, is that you can reuse existing infrastructure such as platforms, wells, and pipelines. So if you look at this, so we need a lot of not new technologies. We need sectors that work together. So we also explored what is now hampering basically these sectors, so companies, but also the institutes that really make this sector integration happen. So we think that we found the four most important aspects. First of all is, of course, economics. We really have to start up a business case for the green and the blue hydrogen. And at this phase, there's some market failure occurring. So that means that on a system level, it's very wise, as we've shown in our system studies for the Netherlands. It's very wise to bring the system integration together, so to work together. It can save billions of euros in the long term. But on the short term, there's no solid business case for this project to start up. So there's really is a valley of death for the early investors. And this kind of market failure, so system value, societal value on the long term, but currently no business case for investors, that should be bridged by incentives or by targets or by other policy interventions. It's a very important barrier. So once we have settled that, and there's a good economic incentive, then we have the issue of the regulatory framework, which in the Netherlands and also across the EU has some important problems. Because from the past, of course, the oil and gas sector and the wind and other sectors, they evolve differently. And also in the regulatory framework, you can see that very clearly. So there's no mention and no clarity of actually where an offshore, for instance, hydrogen production facility would fall under. Is it part of electricity legal framework, or is it part of your oil and gas legal framework? And this insecurity comes, of course, with also challenges in getting permits, but also challenges in getting understanding of what kind of standards and what kind of planning issues you might encounter. One of the examples for the energy islands is rather interesting, is that currently the energy island is not very clear under the international legislation. And that means that there's uncertainty if you have to remove it after you have been basically done with your operations on the energy island. So there's no clarity on actually what you have to do after you're done with operations. Then the fourth, the North Sea is a very busy sea. It doesn't look like it if you stand on the look at it from the coast, but in terms of spatial claims by different users, it's a very busy sea. And then we also have the public that has a very clear opinions and statements on how we should use the North Sea energy. Or on the other side, they do not have a clue what's going on the North Sea in terms of the energy transition. So it's critical, and maybe that's even the most important point, that we have to bring these stakeholders together and understand what their wishes and needs are for this energy transition, and how we can basically streamline the stakeholder perspectives and stakeholders' wishes and bring that into a new design for the energy transition. So that's economics, legal, and stakeholder perception. That comes to the fourth, and maybe integrating the points above. What we really need for the North Sea area is that we get international thinking. So it's thinking across borders, thinking across sectors, and then we really need coordination on that part. So to really bridge these problems and challenges, but also to take these opportunities in offshore hydrogen production, we really have to have a strong coordination from key players in industry, but also from policy. And we think that if we're going to do that, we're going to build this North Sea region into a very interesting, innovative region for the future. So in summary, what are our key research findings up to now? We really need offshore wind. Without it, it's gonna be a very expensive energy transition. Hydrogen has a very important role here to play as one of the options to bring all this offshore wind energy to shore, but also store it in times of low wind and low solar. Offshore hydrogen production can be an interesting part of this equation, but we have to solve we have to keep the offshore installation cost low. That's one of our challenges. Carbon capture and storage also fits into this equation of integrated energy system. And we need a coordinated and cross-sectoral outlook. We need something like a North Sea energy outlook from a European perspective to coordinate all of these opportunities. So what we're going to do in this phase of the program, we just ended the third phase. We're going to now into the fourth phase. We're really going to look into energy hubs in the North Sea. So where are we going to build these innovative systems? So actually places and timelines for these hubs to develop, because we think that's really needed to get the system going. And it also fits, of course, with a roadmap for the whole North Sea to develop further and come with innovative pilots and demonstrations to showcase these technologies, that they actually work and they're actually bankable for the next decades. If you're interested, so of course, this phase of the program, you can still contribute as an in-kind partner or as a membership to get access to all of the results or think along with the research questions, but it's still open. And if you want to know more about the results that I just presented or the other technologies that were not that much discussed today, you can go also to our website, northseaenergy.eu, where you can download all of the reports and also have a deep dive into what you see now on your screen is the North Sea Energy Atlas, where we present basically the spatial energy information for at least now our part of the North Sea, but we're going to expand that also for the whole North Sea area in the next 2 years. So thank you for your attention, and hopefully you have some interesting questions for me to tackle.
Thank you very much, Joris. A very interesting and complete presentation, and certainly presents the North Sea in a way that we really haven't looked at before. I certainly haven't looked at before in terms of its exact resource and tremendous potential. So thanks for the presentation. Yeah, there are a few questions sort of coming in, and so please keep them coming. I guess one of the first questions was around cost, and in terms of how is it that the transporting hydrogen is cheaper than energy transmission? I'm not sure if the question is really how is transport of hydrogen cheaper than electricity transmission, but can you please explain in more detail distance, costs of piping, etc.? So I think it is a question around pipeline versus grid.
Yeah, so in the study, what we compared is basically that you have, for instance, on a platform on the North Sea or on an energy island, you have a high voltage DC installation. So you have a high voltage DC converter with a high voltage DC cable, bringing that high voltage to shore in the Netherlands. And we also have on the energy island hydrogen production by electrolysis and seawater from seawater, and compressing that and bringing it into pipeline and to shore. And here you can see that, of course, the electrolysis has efficiency losses by converting it. So we assume here in our study a 30% loss, so 70% electrolysis efficiency. But you also have that loss if you produce the electrolysis onshore. So there's not much difference in the efficiency onshore versus offshore. But then again, the losses in your pipeline for hydrogen production are very low. You do not lose energy set aside pressure in your hydrogen. But in the electricity grid, so the alternative, there you have losses, especially if you go to longer distances, you have losses in your electricity system by converting from AC from the wind farm to DC on the energy island, and you have electricity losses over the cable. So if you sum those up together, it is wiser to early convert, so to convert nearer to your source, then convert onshore. You save a couple of percentage points in efficiency. And you save also a lot in cost, because this offshore electricity infrastructure is more expensive than laying a new pipeline or you reuse an existing pipeline. So there you understand that if you go further offshore, then this is in favor of hydrogen, So if you move then to 100 and plus kilometers offshore in the North Sea conditions, then it's already wise to start thinking about converting offshore.
Got you. Thank you. Around, I guess, a couple of questions around blue hydrogen. One question around, you said something about lower societal cost of blue hydrogen compared with green hydrogen. That's purely based upon cost. I don't know. I didn't understand either the term societal cost.
Yeah, so we have an energy system model that basically designs the future energy system given some boundary conditions. So we say we have to meet the Paris goals in the Netherlands, and we have several technologies to meet these targets at the lowest societal cost. So if you look at the whole energy system, that's the lowest cost to get all the demand where you want in different sectors and reach the Paris goals of reducing CO2 emissions. And if you run that optimized system model, it can calculate you the lowest societal cost. And in that mix, you have a clearly balanced mix of blue and green hydrogen together, because they both have their pros and cons. Mm-hmm. So it's not necessarily so that blue hydrogen has lower societal cost than green. If I said that, then that's my mistake. But in the balanced mix, you have the lowest societal cost. So basically, it's the best option to have both in the system.
Got you. Okay. Yeah, no, that makes sense. I guess around blue hydrogen, there's still, I mean, blue hydrogen essentially is CCS. So what's the current status of CO2 storage in the Netherlands? Projects and technical capability, etc.
If I can come to this map here.
Yeah.
We have some advanced projects in Portos. That's the project called in the Rotterdam area. So that's our biggest harbor cluster in the Netherlands. And there are plans for blue hydrogen facilities, but also other industrial capture options. But especially blue hydrogen is a big part of the CO2 that's being moved into this area. So there's nearshore depleted gas fields, P18, P15, where CO2 is going to be stored. And this is really active. I mean, investment decisions are very close to be taken here. And injection is already this decade moving into numbers like 7 or maybe even higher megatons of CO2 per year. So there are really interesting developments here in Rotterdam, but also in Den Helder. So that's the northern port. It's a little bit smaller, but also there are plans being shaped here for a blue hydrogen facility, because it's very close to landing points for natural gas coming from the North Sea, and also does access to CO2 transport and storage nearby. So those are really interesting locations for low-cost blue hydrogen production.
And you mentioned partial reuse of infrastructure.
Yeah.
I mean, that's just reversing the flow of the pipes. And what would you? Are there any comments around that infrastructure gain?
Yeah. So what we assume here in the North Sea Energy Program, we've looked at the reuse for hydrogen transport. There are some big trunk lines going through this area of offshore oil and gas production, and they have landing ports here in Den Helder and Eemshaven. And we think we can reuse this this natural gas pipelines for both CO2 and hydrogen, but you can only use it for one, of course.
Yeah.
But for the current CO2 plants, they have new CO2 pipelines. But we think if you look longer, so the next decades, we think we can reuse these offshore pipelines for hydrogen transport to shore. And what it typically saves is that we think it's about 10%, but the jury is not out on that, 10% of laying a new pipeline. And you have to think of €1 million per kilometer here. So you save, depending on distance, you can save that amount. So reuse is about 10-20% maybe of an existing pipeline, and it's €1 million per kilometer. So that's you can easily calculate what you can save then.
Yeah, and I've just actually noticed the legend on this slide that you're showing now. So those darker, those the darker spots are actually storage capacity, but they're clearly, obviously, existing natural gas fields. Now, are they all close to finishing or close to being exhausted?
That's a good question. That's of course the balance between natural gas production depends on natural gas price, and at this moment they're very low. So if this natural gas price proceeds, then probably this CO2 storage capacity will free up sooner than later. But we have in our program have developed basically figures to show for all of these platforms that are linked to the storage fields when they are about to be decommissioned and the cease production. So we have some, they're still vague because they depend on natural gas price, but we have estimates on where they're going out of production, as this is very important for CO2 storage, less so for hydrogen, but it's very important for CO2 storage. But if you look at these fields, that a dominant share of these platforms and fields is going to be offline in the next decade or decades. But the next decades or the next 10 years is critical for selecting these interesting future CO2 hubs and maybe earmarking them for reuse for CO2 storage, for instance, so that they have like a special status that they're being kept for the infrastructure to be used for CO2 storage.
Yeah, understood. Question around the North H2 projects. I think it's Shell and Gasunie, which I think was the bid for offshore wind, was it not? What your thoughts are about that? Specific project, I guess, or is it?
Yeah, those are two a bit different. You have the North H2 project, and that's studying basically installing an electrolyzer here in the northern part of the Netherlands. And yeah, that's a study between Shell and Gasunie to understand basically the business case of installing additional wind capacity offshore, and then either bringing this additional wind as electricity to shore, electricity into the grid, or as hydrogen into the grid, and what is the business case of doing so, and the effect of the energy system. So that's the study of North H2 here in the northern part of Groningen. But we also, and that's the other mentioning you had of the offshore bid with an electrolyzer in it, and that is another project. So that is at this phase, this area, there's a new bid for offshore wind farm area, and a consortium that also has Shell in the consortium. They made a bid that is connected to a big offshore electrolyzer here in the Rotterdam area. So they have basically. They already have an off-taker of this large amount of electricity, and they have this electrolyzer as part of their strategy to have to absorb all this wind energy into the energy system, and also greening the industry by adding green hydrogen.
Talking of off-takers, a question from one. Who'll be following us shortly. What's the estimated total cost for the produced hydrogen per kilogram, and what's the current thinking? Yeah, so
it really is interesting play between electricity prices you see in the electricity system and the electricity prices you allocate to producing green hydrogen. Basically, that sets the hydrogen price. Of course, a big part is the offshore electrolyzer. If you look at offshore production, so that's let's say 50% of the cost, maybe a little bit less. And you have the electricity cost as being a big part of the cost of offshore hydrogen production. So bringing those together, we think that there's a tipping point for green hydrogen at around let's say €4 per kilogram. That's starting to be a point where it's at big scale in the future, when you have already walked down the learning curve for electrolyzers. That's about a figure that we are thinking about right now. So let's say 3.5, €4 per kilogram. And if you move to lower electricity prices for offshore wind, then this comes down a little bit further. But we have to say a lot of innovation has been done already in the last years on bringing the cost of offshore wind down to about 40 euros per megawatt hour. So that's already an achievement, and bringing these down even further is possible. But yeah, you have to be conservative also there. So we think also that import of hydrogen is certainly maybe from Australia, as we've seen in the past presentation, is one of the options that can strengthen basically the supply mix.
Understood. We're keen to stay to schedule, and actually it's a good segue in, because that last question that you answered is from the next person we have on the platform, which is Christian Essers. So I'd like to thank you, Joris. There are some additional questions which we'll look to answer. So if you do have any answers for those, then if you could put those forward. Thanks a lot, Joris, for your presentation. And hopefully you're around, because Bilfinger will be presenting a little bit later, so some further detail around some of that offshore island, which is certainly an interesting concept. Yeah, thank you once again, Joris, and if I can invite Christian Essers up to turn on your video and microphone, and welcome Christian. So Christian is representing Wacker Chemie. So Christian has been working for I think nearly 30 years. He actually reminded me. So originally 8 years in consultancy across multiple different value chains, followed by 10 years in energy and electricity, followed by his now near decade at Wacker Chemie, where he is the director for global energy procurement for Wacker Chemie. So for people that don't know Wacker, it's a 5 billion euro revenue chemicals business. Its main product lines are in products derived from silicon and ethylene, and used across obviously many different end markets, from automobiles to PV panels. So Christian, welcome. And I guess the first question is really around your last question and Joris's response around the 4 euros per kilogram. So Christian, can you just check that you can hear me? We can hear you.
I can hear you. I can hear you all right, and I hope you can hear me also fine.
Yep, you're loud and clear. So
I would bless or punish, depending on your views, you also with the video, but I'm told that the host has disabled my cam.
Okay, I shall just check.
Here we go.
So yes, they may have enabled your camera.
And now, yep.
Should be okay now.
Yes.
Here we go.
Thank you. So yeah, I mean, obviously there are a number of sort of questions, and it's very great that you're here, because clearly, there's obviously lots of talk, lots of projects, but it does come down to money, and it does come down to financing some of these initial projects, and obviously need buyers such as yourselves to be coming to the market. But clearly, you're a major consumer of grey hydrogen. Do you know how much grey hydrogen you actually consume, or?
In our main sites in Germany, we have around 2,500 tons per year.
Mm-hmm.
Plus we have a similar amount, maybe half of that on top on China, which is currently here not at discussion, but so 2,500 tons we need, and we currently produce that via steam reformers. So that is grey hydrogen.
Yeah.
And the price question obviously is important to us, because as a commodity producer, we cannot roll any cost disadvantage through to our products. We have to produce against a global price, and any and all cost elements play a role. So in this sense, for us, hydrogen is an important cost factor, and it's, in a way, it has any green or blue hydrogen has to compete with the current cost of grey hydrogen, which is significantly cheaper than everything we have seen in green or blue offered.
And yeah, I mean, what is that sort of price level? I mean, is it you're talking sort of two euros per kilogram?
It's difficult to compare one-on-one because hydrogen is so relevant for us. We have an N-1 supply, so we always have a backup. But I would say kind of, the €4 per kilogram, that gets us into an area where we will or would seriously consider green hydrogen. That said, the previous panelist mentioned the significance of the capital costs. In our view and in our experience from a project, the electrolyzer cost, the capital costs are really not the driver. The driver is OPEX, and OPEX here means electricity. And for us, an electricity price below 40, actually more 30 to 35 euro per megawatt hour, gives you green hydrogen or hydrogen from an electrolyzer at a competitive cost. But we do know that this is, even given current times, is quite a low price if you talk about a delivered all-in electricity price.
Yeah, that makes sense. I mean, in terms of, I guess, the wider questions of decarbonization on the industry, decarbonization targets, and EU ETS and other influences around price that are impacted upon your business, are there any other incentives for you to pay a premium for green hydrogen?
Currently, we deliver to other businesses, so we are not a kind of a consumer-facing business as such, but we have sometimes 2, sometimes 3 steps of the value chain towards the customer. So for us, a green premium is possible in niche markets or in niche aspects of the business. But when we talk about the majority of the business, it is more commoditized, and our buyers go for the lowest price and are usually not prepared to pay a premium for green.
Gotcha.
This is where it comes. This is where it comes from. We don't have a clear kind of preference for gray. The opposite. We would love to use more green, but then again, you need a significant amount of electricity, green electricity, at a good price to be able to compete with the gray hydrogen, and that's currently the issue. Yeah.
So if green hydrogen is supplied at a price point, coming down maybe south of the €4 per kilogram, you could see obviously Wacker buying and liking to buy that hydrogen. So very much it hinges upon the availability of lots of cheap renewable electricity. In terms of obviously the previous presentation was on offshore wind, and clearly offshore wind is looking for a huge development out in the North Sea. Do you have any comments around that specifically, or you're happy to buy green hydrogen from wherever? So clearly there are projects as far afield as obviously Australia, but obviously there's a lot happening in North Africa, and we see a rise of sort of green hydrogen everywhere. What are your thoughts around that? It's a commodity, and
yeah, it is a commodity, and assuming that the transport issues are resolved, there's no point in denying that that hydrogen can be purchased like other raw materials, as we do purchase other raw materials. We buy large amounts of methanol, ethanol, acetic acid, VAM, etc., you name it. So hydrogen can be transported. The question is in what form you can efficiently transport it without putting a lot of transport cost on top. Liquid hydrogen comes at a temperature that I would call extreme without exaggeration. 20 to 30 degrees Kelvin is no fun. Plus hydrogen has a few other features and characteristics that make it a bit tricky to transport efficiently, or let's say cost efficiently. And I think that's for us the aspect. So we believe that produced closer to the consumption, so that it can be either be made on site, close to site, or transported by pipeline, would be the more decarbonization supporting option.
Okay. In terms of integrating, or I guess PPAs, or rather long-term offtake agreements, are there long-term offtake agreements that you would enter in to help support and give sort of revenue guarantees to potential green hydrogen suppliers? And what do you currently do across the business to decarbonize? Do you have long-term PPAs for electricity, for example?
I mean,
electricity.
We have seriously long-term contracts to secure our supply of hydrogen with company suppliers that produce hydrogen on site, usually combined with a liquid backup, because it's such an essential raw material. So it would not be a problem to enter into a long-term contract, either in terms of electricity converted to hydrogen or straight hydrogen. That's not the point. The point is really that the initial pricing is not really attractive, so puts us off. Plus, there is of course a significant demand and an increased demand, or increasing demand, foreseen for green electricity. Most of the industrial decarbonization options come by way of electrification. So we do already have a significant demand growth expected for green electricity. And on top of that comes the electricity that we need for green hydrogen. Leaving aside blue hydrogen for a moment with CCS, it's an area where I'm just less of an expert. The green hydrogen has the potential to help decarbonization for all users of gray hydrogen. And I think before we get very creative about applications, new applications for hydrogen, we should check where we can directly use electricity. I see, for example, in mobility that there is a significant share of individual mobility that can be helped with electricity, where you simply avoid the losses of energy that you have from a double conversion. Not that it doesn't work, but I would say we have a scarcity of green electricity, so we should use it wisely and go step by step, if you will, the path of decarbonization.
Gotcha. I mean, Wacker is a global business, and you have production sites pretty much spread evenly across Europe, the America, and China. Any sort of comments around the environment and what we've seen in other industries, i.e., carbon leakage, and potential risks or threats to your business?
Well, we do obviously have a risk of carbon leakage. We're part of the commodity industry, so base materials. Base materials are something that are constantly under threat from Chinese and some other energy low-cost regions. And yes, we do see a risk, and it's a de facto carbon leakage on the demand side. It's not that we would kind of pack and go. It's just that we have to compete against companies from, for example, if you take the polysilicon business, we have invest in China. We have companies that work with electricity prices that are half ours, sometimes a third of ours, and they compete in a global market without CO2 cost, and that is an actual risk. If we go for green hydrogen now instead of gray hydrogen, that just adds to the cost disadvantage that we have. This is why so after what's the price per kilogram, and also what's then the underlying electricity price. For us, as I mentioned, 30 to 35 euros per megawatt hour all in into an electrolyzer gives you hydrogen that is competitive. And that does include, because the question usually comes quickly, that does include CO2 cost and everything. It's just something, and electrolyzers are very good if you have varying demands. They have a few advantages over steam reforming installations, but they have to be competitive. And that's currently, I see as a chemical business, we see that as the biggest impediment. It's cost. Technology-wise, most things can be handled, but not on a competitive cost basis.
Just in terms of understanding the function of the CO2 emissions or the permits for that, is that something that's just integrated into the price for grey hydrogen, or you're essentially producing the grey hydrogen on site through your own facilities or through shared facilities or through facilities that you supply?
The grey hydrogen is produced partly on site, and partly it's backed up with liquid hydrogen, which is brought on site. But in both cases, the underlying installations, either on site or elsewhere, are part of the European emission trading system and are thus subject to the CO2 directly. And of course, also for the electricity that they use, where you have the CO2 cost effect.
Yeah. So yeah, if there was a rise in CO2 pricing, then that would impact, obviously, that would hasten the economics of green hydrogen.
Yes, but to give you an idea, if we look at the current electricity prices that we can get at a German site, and we just use the CO2 factor to make the grey hydrogen competitive with green hydrogen, we would currently need CO2 cost of about 200 euros per megawatt hour.
Right. Okay.
Sorry, per ton.
Per ton, yeah.
200 euros per ton, which at the same time would probably kill a number of industrial activities at Wacker and other industrial companies.
Yeah, I mean, that's considerable rise
I know that some people talk about this being the necessary price for the end of phase 4 or the early phase 5, if there is such a thing. But in a short, I mean, just for a scenario, if we reach that in a short time, it would kill a number of activities, and that transformation would be a little bit too fast for us to cope with.
Yeah, I can imagine. I mean, I'd seen, obviously, McKinsey, I think, famously came out with the price being sort of 50 euros would send a signal which would help create change in terms of sort of accelerating the change to green hydrogen or blue hydrogen. Okay, excellent. I think that's, I'm just checking questions from other people in terms of contracts for difference. I'm not sure that's relevant for your business. In terms of the actual mechanics or the actual plant equipment that you have on your balance sheet, I mean, is there some existing assets that have been amortized? Is there any other inhibitions to changing from sort of steam methane reforming to electrolysis, or you're continually improving in developing project and new capital, etc.?
I mean, we have looked as recently as last year, 2019. We have looked into a project where we thought about replacing the existing steam reforming equipment with 2 electrolyzers. It would have been possible. It would have been technically under control, but the electricity price outlook from 2019 over a possible 10 to 15 year horizon was not at a level that we could possibly make hydrogen on a competitive level. We have therefore prolonged the life of the existing asset, which is actually not on our balance sheet, but on the supplier's balance sheet. But that is a minor thing. You pay for it one or the other. So we keep the flexibility to look into this thing again over the next 4 to 5 years. And if we can secure electricity for a longer period at the levels, to beat this one to death at the levels mentioned, would be an option. And we would certainly do this on a short notice.
Excellent. Well, that's great. Thank you for joining us. Thank you for sharing your viewpoint. Very important voice of reason, and but also equally, I think, encouraging. I think, yeah, it is about getting the economics to work, and trying to achieve the economies of scale. And I would certainly imagine the initial grey hydrogen users would be the low-hanging fruit, and should be the first sort of targets of the rising clean hydrogen industry. So we'll be watching this space, and I'm sure you'll be watching this space too, Christian. So thank you very much for sharing your thoughts with us and taking time out of your day. I hope you stick around and find the following presentations interesting.
Thank you very much.
Cheers, take care. Many thanks. We're going to take a short break now, and we ask everyone to join us at 11:30 when the conference sponsor, Smart Energy, will be giving a presentation. So Christian Foduk, the Managing Director for Projects, will be joining us at 11:30. We'll be following that with a presentation from Bilfinger on their energy islands concept, and then having a panel discussion, taking your questions around those two presentations. So yeah, go and grab a coffee, take some time out, and we look forward to you being back here in half an hour. So many thanks, everybody. Bye-bye.